Okay. And if you ever miss that first QR code, you can usually come up to me later. I won't let you actually see the question usually, but I'll just snap it. Okay. And so what we're going to do here is, are we have it recording? Yes. Okay. Okay. So remember that when we're doing math, we can always multiply anything by 1. Okay. And so what we have here is oftentimes we're going to use something called equivalent units. Okay. And they're called equivalencies. What they are is they're actually the same thing that equals each other. Okay. It's kind of like saying I have $1,000. That would equal 1K, right? It's the same thing, isn't it? And so I say I have 1 deciliter. That means I have 0.1 liters, doesn't it? And so it's actually just the exact same thing, isn't it? Okay. And if we have a deciliter, then we can set those up in what are called unit conversions, okay, or conversion factors. And so the conversion factor is just going to be an equivalency expressed one above the other. Because they're the same thing, all I'm saying here is this is just 1, isn't it? This would be dividing $1,000 by 1K. Okay? It's same thing. And so I can take a conversion factor and I can put it either direction. I can have the deciliters on top, and then liters would be on bottom. And again, that's just overall the same thing. It would cancel out, right? Or I can have the liters on top and the deciliters on top, okay? And these are very, very useful when you're trying to convert from one unit system to another. And this is how you're going to do what's called dimensional analysis, okay, or unit conversions. And so, very useful. Now, when you do this, one of the things I want you to remember is whenever you do these dimensional analysis unit conversions, you're going to be taking things, and almost everything you put in is just going to be equalities, these conversion factors, meaning you're just multiplying it by 1, right? Okay. And you know these are always true because they're just equalities, right? And so you can't just like make things up that don't make any sense. Just because I want to go from kilograms to miles doesn't mean I can go 1 kilogram is equal to 1 mile. It's not, right? Like these are actually equalities, right? Deciliter means 1/10 of a liter. That's the meaning. Okay. And so you got to be very aware of that whenever you're doing the problems later, okay? Is that I'm always stating something that I've either been given or is an equality, okay? I'm not just stating numbers. All right. So this again is going to be dimensional analysis is what it's called because professors and teachers want to sound fancy of what they're teaching. It used to be called unit conversions because people had less egos. It's not fancy. We don't need a however many syllables that one is word for it. But this is the steps for any given problem. I'm not going to ever say those again. I put those up because oftentimes some people find those useful. I personally, and about 70% of the classes people I've taught don't actually benefit from using that. Okay? So it's kind of dependent on try it one way, try it the next way, see what works for you, okay? I find more often than not the people that do try to use this at the beginning end up not being able to do problems if they're reversed or there's slight differences to them, even if it's just like one additional step in the front, because it's not step 1. And now they're cooked, okay? Significant figures. The best way I can explain significant figures is significant figures are going to be used to tell you where your uncertainty is. Okay? So you're going to have a digit that you're certain at. Okay? So for example, let's say we're talking about counting out money, right? And you've counted all the dollar bills really well. And so you're certain for those dollar bills. But you didn't count the change and every individual penny. You just estimated. I think I have like 70 cents-ish, right? I might have 80, might have 90, Might have 60. Don't know. Okay. And so what am I going to represent that as? Well, I got the dollar numbers really well, right? So I have $1,125. Okay. Know that number. I'm good. How much cents do I have? I think I have 70 cents. I have a, pretty decent memory of that and understanding of that. Okay. And so this next number, you can represent it like that if you have an idea. But that's the one you don't know. Okay. You don't know that number. This is the last number. This represents where your uncertainty is. Okay. So I am certain up to this number. I am uncertain after that, right? Everything after this, if I try going 3, 2, 1, these are BS numbers. I don't know how many hundreds of pennies is in my bank account. Doesn't even show it on the portal, right? There is a number, actually. My bank account literally has this hundredth of a penny number in it. Do you guys know that? Yeah, we'll talk a little bit more about bank calculations as we go along, but banks actually calculate down to like the hundredths of pennies. Okay. Now, the banks actually would take that next number and they steal. So, like, you would have your interest in your savings account calculated. It's not going to calculate to a nice round number, right? It would have fractions of pennies. And so they keep that fractions of pennies in your account essentially as a number you don't see, but it's there. And that way they don't steal, too much that makes you angry. Hey, I should have been 1 here and now I'm, 0. Why am I 0? I did my calculation. I know you stole a penny. You might get angry at that, right? If it's a number you don't see and you don't even think about because the numbers don't go down that far in many, you don't care. Okay? Now, a funny thing about this is a perfect allegory for uncertainty, right? So, like, if you look at your bank account, you're certain to this if you look at it, right? And so that would be the last one that you would have some degree of uncertainty for because it could change tomorrow just a little bit, enough to change it, right? This next digit, you don't know at all because you don't see it. Okay, you can't estimate it at all, right? And then your bank actually, when it does the calculations, it does all these calculations down to like 6th or 8th decimal place short numbers, okay? Because calculators can do that very easy, right? And then what happens is it just rounds everything after this digit away because this is the last one it can get away with just taking these. And it always rounds them down. Okay. Now, there's a funny thing that's happened a number of times through history, actually, quite a few times now. Happened about 10 years ago from a Ukrainian hacker group did it. They hacked the ATM system for a very large chain of banks in California. Okay. It happened in the 1980s and the 1990s as well by other groups that did it. The Ukrainian group actually got away with about almost $400 million. 300 something million dollars over 3 days. Okay. And so what they did, by the way, there's several movies. Office Space has this, but they screw it up because it's a comedy and it's funny. Superman 2, back the old Superman 2 from like the 1980s or something, 1970s, I think, actually, has this as a plot. So what the hacker groups do is your bank is calculating down here somewhere, right? And so what their program does is they infect the bank and they have a little program. It takes this digit and it steals that one. Okay. And so the bank doesn't notice for a long time usually. It usually takes them something like months to notice because it does compound over time and make a difference. But they steal that money and they put it in their own account that's overseas and can't be seized either. Okay. Sometimes they use crypto, sometimes they use other things, but crypto is actually not easy to cash out. Now, that doesn't sound like a lot, right? We're talking like hundreds of thousands of a penny sort of stuff, right? Not much. But what happens when you do that hundreds of millions of times a day? Hundreds of millions of times a second. Big banks, they do these calculations every second of the day. They're doing millions of these, okay? And so this stuff adds up incredibly fast. And in Office Space, they stole like millions of dollars over the course of a day because they messed up the digit. But the hacker group actually stole the 300 something, almost $400 million in 3 days because it's just a huge chain of banks, a lot of calculations. It's many, many times a day, right? And nobody even realized it until months later. And so, dang, right? Anyways, that's an actual application of people messing up significant figures and actual significant figures making a difference in the world, right? Now, in science, this is typically going to center around our uncertainty in our use of instruments and our measurements we make, those sort of things, okay? And so when you're measuring matter, it's going to rely on the precision of your instrument that you use to measure it. You can use like a laser distance finder, or you could use a tape measure, right? Laser ones are typically much better than the tape measures because people don't use the calibration piece on the end properly, and they get worn out and they just start like flopping everywhere. They have like another eighth of an inch to a quarter of an inch. You're off. So it's important to report calculated answers reasonably. If I report, I think I have $1,000 in my account. Should I spend $1,000? Should I even get close to that? No, I'm probably going to go over if I do, right? I could have $800. But if I say I have $1,125.73, I can spend $1,125 and I still won't go over one because I know all those digits. Okay. And it's kind of like if somebody were to deposit, I deposited a few $100. Would you spend $300 if your account was zeroed before? No. No. You don't know if they meant like 200 something, right? Or 300 something, or they could have been 400, who knows, right? And you don't have the significant figures, right? No. When you're reading measurements from a non-digital device, there's going to be some level of uncertainty in the measurement itself. So if you've ever used a ruler or a tape measure and you measure and then you measure again and come up with a different number, that's what I'm talking about. That was your uncertainty. That difference in those numbers you're measuring, those were your uncertainties, okay? That's the digit you can't be quite certain about, okay? The one that you like, the 37 inches, you can be certain of that. The 1/16 or 3/16, and you came up with different ones each time, those are the uncertain, right? You still want to report it. It's still data, and you have an idea. It's the lower quarter, so you're under a fourth, right? But you're uncertain about that digit. Okay, it could have some flex. Now, in any measurement, our significant figures are going to be the digits that we know with certainty plus one estimated digit. So you always want to give a measurement whenever you're giving these. That are manual measurements. Analog is usually what it's called. That would be the one I'm certain about. So 37 inches. And then I'd want to give my best estimate for the next one. And so I think it's probably, I came up with 1 3/16. Probably 2/16 or something, right? And so it'd be 37 inches and 2/16 of an inch. Okay? And that's what I'd give as my measurement. And what does that communicate to you all? Well, he's sure about the 37 inches, right? Because he went one more. Okay? He went a little bit further. The 2/16 of an inch, I'm communicating you, I'm uncertain about that. Okay? If I was to go another digit over, I'm going to do decimal places now, if that's okay. Everybody okay with centimeters? It's a little bit more difficult. So if I gave you, let's just do this in centimeters. If I gave you that, I'm uncertain here, right? At the point 2. If I gave you this number instead, I've taken a ruler and I've measured that down to like millimeter sort of scales, right? And so I've taken that extra effort. I'm now certain of this one, not so certain of that. Okay. And so if I keep going and I use more and more and more accurate devices, I communicate that by adding more significant figures, right? Okay. If I use less accurate devices, I communicate that to you by giving you my last digit that I have any degree of knowledge about. Okay, that I'm uncertain of. So this measurement would have been winging it with the tape measure, and I couldn't come up with a consistent centimeters. Right, my tape measure is broken, not working right. I'm having issues. Okay. If I was to use this right here, I would be not even accurate to within 1 cup, right? If I made you pancakes using this, it wouldn't turn out so good, would it? It'd be very runny, probably. Okay, so digital devices are quite nice. This is why for $20 I bought myself a nice laser one, because I'm tired of my damn tape measure coming out wrong all the time. And so digital devices, the manufacturer has went ahead and done that significant digit error for you. Okay. And so the last digit on a digital device is typically going to be the last one where you have that uncertainty. Okay. And all the ones before that are going to be the certain. And so they've kind of done it before you, though honestly, a lot of digital devices, they don't even put in the uncertain digit on. They just give you all certain digits. They don't usually tell you that, though. But it's funny because you can usually go into settings and then you can like tell it to give you that next one. But the in the labs, the last digit, that's going to be on the uncertain digit. Okay, because all of ours are calibrated like that. Now, in any measurement, all non-zero numbers are considered significant. If you have a non-zero number, it's automatically going to be considered significant, because the only reason you would put a non-zero number in this is because it's significant, right? I don't have to put a 7 there, do I? If it was 30, I put a 30, right? Okay. Zeros are different, though, aren't they? Zeros represent two things. They can represent the actual number. They can also represent a placeholder, right? Can I write this? Is that 30? No. No. I need to put that 0, don't I? I have to. And so that's called a placeholder. Okay? And it kind of complicates the entire significant figure situation, doesn't it? Because when we hit a 0, when we see a 0, it could be a placeholder or it could be a significant figure. Okay? And so they're going to be your troublemakers. If you have a 0 and a number without a decimal point, it's going to be significant, and it's significant. You're going to show this by doing one of two things. You can put a decimal point, in which case that tells you that that 0 is significant, and that's my last digit that I have that uncertainty. Okay? Without that, I'm actually saying I don't really know this one. Okay? So I'm like $30-ish. Could be 40, could be 20. Okay? It's something that rounds to 30, right? Could be 35, could be. Okay? Now, when I start going on here, you can also go like this. Okay? And that tells you that 0 is significant. Right? So let's say I had like 3,000, and I'm something that rounds to 3,000. I know that. I don't know if I'm 2,800 or 3,100. I just got payments that should process. I don't know if they've hit yet. Okay. And so that's how you'd represent that. I would say that, I'm 3,000. I kind of know my hundreds, but it could be off just by a little. Like I could be $50 plus or minus, right? And so I don't know if the $20 check cleared yet. I don't know. Okay. And so that's what I'm communicating to you. If I put lines that include that, I'm communicating to you, I don't know the dollars, right? I could be like $3,005. Okay. But I know the tens, I have an idea. I know it rounds to that. Okay. Okay. And so if we have the significant zeros and large numbers, you want to draw the line above them if they're significant. That's the easiest way to deal with that. If we have exact numbers, they're counted as being an infinite number of significant figures. An exact number would be a thing like the number of students in this class, the number of ears you have, the number of toes you have. You probably can count those and not have a problem. The number of fingers you have. And, those are definite things that you don't have parts of, right? You don't have a part of a person. There's not a half person. Okay? No quarter people in that. None of that stuff. Okay? There is not a half desk in here. There's whole desks and purely the number of desks, right? Not going to get half desk, a quarter of a desk, whatever. And so those are always exact numbers. Definitionally, anytime we have a definitional number, like decimeters, that's going to be exact numbers as well. Okay? Because you can never be anything else because by the definition of it, a decimeter is 1/10 of a meter, right? And so there's 10 decimeters in a meter. It's never 11. It's never 10.5. It's 10. Okay? It can't be anything else. So let's do some examples right here, which is usually the easiest way to figure this out. And so, for example, this is no zeros. We have 1, 2 digits. And so that is 2 significant figures, is what we call it. Okay? Let's try this one. We have 1, 2, 3 digits, right? None of them are zeros. And so that's 3 significant figures. Okay. Now, how about this one? This one has 3 digits in it, right? That 0 right there is in the middle. Okay, now that 0 is not actually just a placeholder, is it? I could have put a 1, I could have put a 2, I could have put any number, right? And so that is a significant figure. And so, if you have no decimal places, okay, what you're going to do is you're going to start over here. You're then going to trace yourself over to getting bigger and bigger numbers. Okay, remember this is no decimal place. So the first non-zero number you encounter, everything after that is significant figures. So this is a significant figure because it's a 1, right? And then we go here, well, it's after the 1 is. And so that's significant. Okay? And then that's a significant figure as well. It's 1. So we have 3 significant figures, don't we? Okay? Okay. So let's look at something that has a decimal place now. Now, if we have a decimal place, we actually start on the other side. Okay? And so we're going to start on this side. The first non-zero number we encounter, everything with that one and after is going to be significant. Okay? And so we counter a 6 right away. That's significant. The 0 has to be significant now because it's after the 6. And 7, 1, those are all significant. And so we'll have 4 significant figures. Okay? Okay, let's try the next one. Do you see that decimal place? Okay. And so the decimal place says we should start that direction, right? And so we have a 2, that's a non-zero number. And so significant, and then the 0 is significant as well because that's after that 2. Okay? And that's going to be 2 significant figures. This one right here, again, we have the decimal place, right? So we start on this side, and we start tracing along. And so 9, 8, significant. The zeros are after the significant figures, so they're also significant.
Mm-hmm. Well, I do have a question for that one. It's just like that one. It's like you can pick out the zeros. Nothing changes the value.
Yes.
It's still 9.8.
Mhm.
So why is 0 still considered?
That's why it's considered significant. Okay, so first off, the value doesn't change. You didn't have to put the zeros, right? And so they're not placeholders. Okay. And so what you're seeing here is I could have put 9.8, right? Okay. But that means that I didn't know if this was exactly right, right? So I'm telling you that I have a number that averages out to 9.8. And sometimes when I measure it, I get 9.75. Sometimes I measure it, I get 9.85, right? And I kind of bob around there, okay? By putting these extra 2 zeros, what I'm telling you now is I measure this out and I get like a 9.8005. I get a 9.7995. Okay. And so I am certain about all of these digits up to this one. Okay. I know all of these ones here with absolute certainty. So, like, degrees Celsius, this isn't going to make much sense to you because the slight changes in temperature you don't care about. But, like, if this was like feet that you have to travel, that'd be extra steps, right? And if you only brought enough rope to scale a 9,800 foot cliff, and then it was an extra 5 feet, you're gonna be very, very angry, right? Or if you did it with money, right? You wouldn't maybe know that last $5. Okay. And so somebody went, yeah, I'll sell you this car for $9,800. And then you came, showed up, you had $9,800 and went, no, you need $9,805. You're going to be kind of pissed, aren't you?
Yeah.
Yeah. And so that's the certainty, right? Saying 9,800 period dollars is different than saying 9,800-ish dollars. Okay? And that's what I'm communicating there. Okay, so let's look at when zeros are not significant. Okay? So right here we have decimal places. And so we're going to start on the left. And these are zero numbers, right? We don't have any non-zero numbers yet. We only have a non-zero number right there. And so that's going to be one significant figure there because that's our first non-zero number, right? The zeros are placeholders. You can't get rid of those zeros without changing that number. That's the only purpose they serve. This right here is going to be, again, all of these are not significant zeros. And these are the only significant digits right here, which is 2 and 4. Because those are my first non-zero numbers again, right? Okay, so this one has no decimal place. So we start on this right side, and then we trace over. And these are all zeros, so we ignore those. And then 2 and 1, and those are our significant figures. So we have 2 of them, 2 sig figs. And over here, we go up, and we get 5. That's our first significant figure. And so 5, 4, 3, and that's 3 significant figures. Okay, everybody seeing the pattern and got a little practice on your belt? Okay, good. There's homework. You'll do it. I make you do everything. All options you could possibly need to know to solve these problems, right? All right. So, by the way, if you ever go like, Dr. Clausen, you didn't show us this problem on homework. First off, yes, I did. Maybe in reverse, but I did. But if you ever say that, just understand what you're actually asking me is, please, Dr. Clausen, double or triple the size of the homework. That's what you're actually asking. Because if you haven't seen that in the homework, that means I have to add more stuff in the homework, right? So that's one of the things I always find really funny when people say that. So calculating numbers and rounding. Now, you have been taught how to round. Mostly it was right, except for probably one thing that was wrong. Okay, which is really funny now. So you're going to add, subtract, and multiply or dividing. Again, they can oftentimes end up with numbers that has too many digits, right? They're not all significant figures. You don't have to write them all. You don't need 20 digits, right? Very rarely. So manipulating these measurements with arithmetic they don't actually increase their certainty. Just because you did some arithmetic does not mean you now know that number better, right? If I estimate the distance to my house, it's about 2 miles. Just because I go, well, if I go back and forth twice times 2, that doesn't make it more accurate. It actually makes it even worse, doesn't it? Because now I am probably twice as wrong. But it doesn't help the number. It doesn't make it more sig figs, right? And so we need to keep in mind that that does not change your number of sig figs just doing arithmetic, period. Just because your calculator says 20 digits or 8 digits after didn't increase the certainty of your measurements, right? Now, the answer can never be any more certain than the least certain number in your calculation, okay? Now, this means slightly different things when we do addition and subtraction versus multiplication and division, okay? Now, addition and subtraction. Let's say I go back to my bank account, right? Do I even really care that the bank stole, 1/100th of a penny from me? Am I noticing that? Am I like banging on the door of the bank? No, it's not worth my time. Don't care. Don't even know, right? And so, if I add or subtract, if I was to go, hey, I'm going to pay you $0.00001. Go ahead and do a 30 minutes work for me. Are you going to do it? No. Why are you not going to do it? No. Not going to change your account, right? Okay? It's not even going to show up in the numbers, is it? My certainty is less than that, okay? And so if you add or subtract a very small number, it's just not going to show up because your uncertainty is greater than that, okay? If you add or subtract anything that's lower decimal place than your uncertainty, not going to show up. So when you do addition and subtraction, it's only the thing that has the least number of decimal places that shows up. Okay? That's where your uncertainty is. Right? Just like the example of somebody told you they added $1,000 to your account, but you don't know if it's 800 or it could be 1,200. You have no idea. So your uncertainty now is in the hundreds place, isn't it? You can't spend those hundreds of dollars. You might overdraft. Okay? Same thing here. You've lost that certainty for your smaller number that you knew. Okay? Now, multiplication and division is going to be a bit different. So what instead of adding that number, okay, you don't care if I add that or subtract that number, do you? Too small. Doesn't matter. What if I multiply? Multiply by your bank account by that. You're really going to care, right? You're going to have pennies left in your bank account by the time I'm done with you. By the way, if you think about this, so you'd have 0.001%. That's an average loss on bad crypto investment. 99.99% loss, right? There you go. You invested it in some crappy crypto. And now that's what you got left. So that's your uncertainty now there, right? So what's going to happen on that is when you do the multiplication or division, what you're going to do is you count the number of sig figs, okay? In this case, this had one sig fig, okay? So my resulting end number is going to have one sig fig. Because if I have more sig figs, I'm going to get out more stuff from that, right? More information, okay? And so that's what's going to end up being for multiplication and division, okay? You don't care about the size of the number. Big numbers make it really big if it's multiplied, divide. Well, divide makes it very small. Small numbers and multiply make it very small, right? If you divided by that number, you'd be really happy with me because you'd be a millionaire, right? Okay. Now, let's talk about the rules for rounding. If it's 4 or less when you're trying to round, you're going to round whenever you do these arithmetic operations. You'll get your degree of uncertainty here. So we had our degree of uncertainty here, right? Which is this one right here. We then added this number right here. Okay. And so whenever we do this, we're going to come down here, and this is less than 4, isn't it? 2 there. And so we're just going to round that down, and our new number is going to be, right? And so we rounded down, and now we have the correct number of sig figs. Okay? So whenever we do these roundings, 4 or less, round down. If we have 6 or more, you should always round up. Your book says to round up at 5 or more. Okay, 5 or greater. Is that what everybody was taught back in like high school and all that in most of your math classes? That's actually wrong. So if you round up at 5 or more every time, if you do that a bunch of times, one after another, what will happen is you'll get a value that's way too big. Okay? So like if your bank account did that with your payments every time, you should be very mad at them. Okay? Because then you'd always be paying more and more and more and more and more, right? Or if they compounded your interest on your debts like that, you'd be very, very angry, right? And so what you actually want to do here, if you're going to do this properly, for tests, it won't matter because we're multiple choice all the time. For your book and answers in your problems, just go ahead and round up for 5. But if you get out in the real world and you start actually doing jobs, what you always want to do is you actually want to round up half the time, round down half the time. How you do this is you would have numbers like 0.15, 3, 0.15, okay, so what you do is you choose one of these, and every time the next digit is odd, you round one way. Every time the next digit is even, you round the other. Okay? Most people do this odd up, even down. Okay? And so this would be rounding to this digit right here. And so this would be 0.2. This would be 0.0. Okay? And so up, odd, down evens. Really, as long as you do it consistently, so you get half and half, you're good. What you're doing is you're trying to cancel off those roundings. Okay? So that you round up half the time, down half the time, they cancel each other out. Okay? Okay. Now, whenever you do calculations and you have to do multiple steps, you need to take as many digits as you can into the next step. Okay? The general rule is to take 2 extra digits. Okay? So instead of cutting it off at 2 decimal places, you instead cut it off at like 4 decimal places or 5 decimal places. Okay? Because if you take and round every single time, then what's going to happen is you're going to end up with numbers that are significantly different at the end than what they should be, right? And you'll know this is happening because you'll always be a few decimal places off. Okay, you'll always be at least 1 decimal place off every single time you do a problem. And you go, why am I always a little off? This is why. You're rounding every time. You need to give it 2 more digits. Okay? And then round it at the end to get your correct number of sig figs. Right? Don't round it every step. Now, scientific notations. In scientific notation, we're going to have something called a coefficient. This is the C in front. This is going to be then in the form of times 10 to the power of. This power right here can be positive or negative. We can have it a positive 2. We can have it a negative 3. Okay? They can be any of those. This coefficient has to be a number between 1 and 10. You never want a 10 here. You never want an 11. You never want 100. Nothing like that, okay? You want like a 9 point something. And it should never be a number less than 1. So you always want like a 1.0, 1.3, that sort of stuff. Never a 0.9, okay? And the reason you want that is anytime you get those numbers that are 10 or a point something, you should have had that in this tens right here, right? Okay. And so this is a very, very convenient way to do scientific numbers. One of the big reasons is this coefficient right here will always be in scientific notation. There is no placeholder zeros if you write this in scientific notation. It's always going to have the correct number of significant figures. Okay? And so here's some examples of these. This would be 1 million, right? When we see 1 million, well, it means is 10 times 10 times 10 times 10, 6 times, right? And so this can be rewritten to the scientific notation. That would be 1 times 10 to the 6th. Okay? And so that would be 1 million in scientific notation. Now you'll notice there's a very easy way to do this, however many zeros you have here. That's the scientific notation, right? So 6 zeros here. 6. Okay, so 1 is kind of interesting. Some of you may or may not know this. 1 times 10 to the 0, anything to the power of 0, is 1. And so that's just 1 times 1. Okay. You don't normally write that out in scientific notation. You just write the number. So if it's 1, it's just 1. If it's 1.05, it's 1.05. You don't write times 10 to the 0. Okay. Because it's just a waste of time then. Now, one of the things you'll appreciate is this is a lot more effort once you start getting extremely large numbers or small numbers to write out than this is, right? So it saves you a lot of time and effort. So if you were to write out something like 10 to the 34th, that would be a very, very long thing to write, right? It would take up like a third of a page, okay? This does not take up a third of a page. Okay, this would just be 34 up here, right? Okay, and so this is 1 over a million, and that's 10 to the negative 6. Yeah, that's not micro, by the way. That's in micrometer. All right, so the percentages. Another way of representing percentages would be parts per hundred. You may hear that sometime. And so percentages are represented by the percent symbol. And it's going to be the parts out of 100 total. And so it's a hundredths. The percent is going to allow us to directly compare two sets of numbers that have different total sizes. And so we can get like percentage, right? Like I got 50% right on this test. I got 50% right on that test. They could have 50 questions on one and 30 questions on the other, right? Okay. So the percent is always calculated by taking the part that you're looking at, divided by the whole, and then times 100. Okay. So I got 20 questions correct out of 30 possible questions times 100. That gives me my percent correct on the exam, right? And so 66.6 repeating percent. 2/3. If we have this right here with a fraction, this can be converted to percent by just dividing the numerator by the denominator, multiply by 100, and then put a percent sign. If anybody ever writes a percent right there, what they mean is it's units of percent. You're getting percent out. Okay? You do not put this part divided by whole times 100, take your calculator, then hit percent. Okay? What the percent button does is it does times 100. So that would be times 1,000 or 10,000. You'd be very off. Okay. And so the decimal number, this can be converted to a percentage by multiplying 100. So if you had a 0.6, what would you have in terms of percent? 60%. Exactly. It's absolutely correct. Okay. And so this is mass. If I say I have 1 of something, okay, then what does that mean? Do I have a lot of something or a little something? Did it have any meaning? It didn't, did it? What am I lacking? I'm lacking units, right? That gives you context. So in science, we always have to have a number and a unit, right? Without that combination, I don't have any context for what I'm looking at, okay? So I could have 1 star, 1 sun. Now, a lot of something, right? I could have 1 feather. I have a little of something. Okay? I could have 1 kilodollar. I have a moderate amount of money. $1,000, right? It's not bad. I could have 1 penny. My total net worth. 1 penny. That's gonna be problematic, probably, right? I can't even get something to eat. Okay? And so very different numbers, all ones, right? So we need our units, and we're going to start developing these units now. Okay? Now, mass. This is going to be anything that takes up space and can be placed on a scale and weighed. This is going to have mass to it. And mass is going to be a measure of the amount of material in an object. This is a circular definition. If you're like, that's very unfulfilling, Dr. Clausen, that's fair. That's fair. It is most common definition in textbooks. I have a better definition for you that has been floating around in the scientific community, kind of bumping itself around. And that is that it's essentially inertia in space. Okay? So if I, for example, I'm a much less mass than the planet, push against the planet doesn't move a lot. But I push against the planet, and I move quite a bit, don't I? Okay? And so that's your mass acting. Now, the common unit that's used to measure mass is going to be gram, and that's G. The weight of an object is going to be determined by the pull of gravity. So in this case, the pull of the planet Earth's gravity on your mass. That gives you weight. Okay? And weight is actually a force. All right? And so this is going to change based on location. If you were to like go up onto a very high mountain, your weight would go down a little bit. If you were to go lower, your weight would go down, up a little bit, not a lot. If you go up into space far enough, right, you develop weightlessness. You don't feel any force from the planet anymore. Okay, go to the moon, you actually experience the pull of gravity by the moon instead, right? And so you see the astronauts jumping along, right? Leap, leap, leap. Yeah. And so very little gravity. Simply hitting a golf ball on the moon is enough to launch it off the face of the moon, off into space. Nothingness. Now, in terms of mass does not change based on location. The astronaut, when he's in space, he can't push against a feather, right? Or she can't. She can't push against a wall, like a little drop of liquid and then move herself. Okay? She has to push against something that weighs a lot, doesn't she? And so, like, push off against the station, they can move, right? And that's because of your mass differential. Okay? Weight 0. Mass still the same. All right. Now, as long as the object that's being weighed is roughly in the same location on Earth's surface, its mass and weight will have the same measured value, won't change. If you're measuring mass in different locations, you will need new equipment to do it, but you will still get the same mass. In terms of weight, though, they would change based on location. Okay? If you're just doing it on the surface of Earth, it doesn't change that much. You probably won't care, to be honest. But a lot of scales actually have like a correction factor. They do. So in the lab, we will use mass and weight pretty much interchangeably because they're all going to be in the lab on the same balances, right? And you'll use the same balance all the time. And so weight and mass will be the same for you. Now, volume, this is going to be a three-dimensional measure of space that's occupied by matter. In our lab, our volumes are going to be routinely measured with a graduated cylinder or a pipette. Those are our usual ones we use. We do not use a beaker or an Erlenmeyer flask. It would be like trying to make your pancakes with this container right here. I can't measure accurately enough to actually do it, right? Same thing in the lab, okay? So the units typically going to be used in the lab will be milliliters. That's 1,000th of a liter. In the clinical setting, the volumes are oftentimes going to be measured with calibrated syringes, this being a syringe right here. They sometimes measure milliliters, but more often than not, they'll be cc or centimeters cubed. All three of these units are the same amount of volume. Okay. And so they're actually the same thing. They're equivalent to each other. If you get a teaspoon, however, that is 5 milliliters. Okay. If you get coffees from other countries, that's always a problem for me. I have a little conversion chart that I've done the conversion for 1 scoop, and I know what that scoop is. Densities. Density small d is the abbreviation, not capital D. This is a comparison of 2 units. That is going to be the mass compared to its volume. So this right here is the formula. We have density, which is lowercase d, that equals lowercase m, which is mass, divided by capital V, which is volume. Capital M is not mass, by the way. It's a whole different unit. We won't cover that for a little bit because you need some other concepts. Now, if we look at water, water has a density of 1 gram per 1 milliliter. And so this is going to be 1 gram per milliliter. Okay. You have 10 milliliters, you have 10 grams of water, don't you? All right, so you may know this, but if something is less dense than water, then what happens? It floats, yeah. And we can actually see that right there. If something's more dense than water, what happens? It sinks, yeah. And so water's density is really important for us on the planet, right? Whether it floats or sinks in water, very important. And so there is actually a specific unit for that, which is called specific gravity. Okay? And specific gravity is going to be used most often for liquid densities, actually, to see whether it's going to float on top or sink. And if not, will it equilibrate? Okay? And so the density of water being 1 gram per milliliter. By the way, notice we've been very careful here with our sig figs. 1.00. If you went another sig fig, it would actually not be 1. It would be 0.99999. This is at 4 degrees Celsius. It does change with temperature, not a huge amount, but it does. So if you heat water, you'll see it'll overflow if it's too close to the top. Now, this is close to that value at body temperature. Body temperature, it's pretty close to 1. It's a little bit higher, but not enough for you to really see in this case. So the ratio of density of a sample to the density of water, this is going to be called specific gravity. It's abbreviated SPGR. And so it's going to be, again, density of the whatever you're looking at, the sample. It could be urine, it could be a metal piece, it could be wood, whatever. Okay? Sugar water, whatever. Then you divide it by the density of water. What you'll notice is they have the same units. So you will actually end up canceling all your units, and you'll get a unitless number. That's specific gravity. Now, there is a pretty easy to use instrument that's meant to do this, and that is the refractometer. And this is a very, very common piece of equipment to see in like a clinic or like a medical environment. Okay, because there's a whole host of testing that's very cheap to do that uses specific gravity against water. And for example, urine, if the specific gravity is too high or too low, then you've significantly deviated, and you probably have things like ketosis or diabetes. Okay, and so it's a very good indicator for this. And then they can get you in for more expensive testing. Okay, so very common testing to do, very quick, easy, very cheap, which is good. Temperatures. So we measure temperature of a substance to determine the hotness or coldness. If that feels utterly unfulfilling for a definition, it's because it's entirely circular, isn't it? What's hotness and coldness? Measure temperature. And so the real definition for temperature is it's actually a measurement of randomized kinetic energy. Okay? So if you have kinetic energy, right, that would be like throwing this. It's traveling through space. It has a certain amount of mass and speed, right? Kinetic energy. Okay, what if you have 2 objects moving in different directions? What if you have 10 objects, 100 objects, a million objects, billion times a billion objects? It gets undoable, right? And they could all have different speeds. They can have different masses. It's unachievable. So what you do is you then do what's called randomized kinetic energy, and now we call it temperature. And that's how we measure it. Okay, so all that is just kinetic energy of all the particles moving in random directions. Okay, now you can use thermometers to measure temperature. You can also use an electronic probe or electronic thermometer to measure temperatures. In the United States, we'll use the Fahrenheit scale. It's degrees Fahrenheit. The rest of the world uses degrees Celsius, though sometimes the degrees Fahrenheit pops up in other countries here and there. Usually, though, they use both systems, so they're going to use that. They don't just use Fahrenheit. The United States is very unusual that. This is one scale that if we're talking like we should switch to this, I don't really care about the distances. It's a little annoying for using inches. The temperature scale actually is the one I like. I like the Celsius. 0 degrees Celsius, water freezes. Okay? 100 degrees Celsius, water boils, right? And that's nice. Easy. Makes sense. Okay? If it's 0 degrees Celsius out, I know water's freezing. Okay? That makes sense. Now, the scientists, we actually use another scale. So degrees indicates to you that this is not something that they have a 0 point that actually means something. Okay? And so we've arbitrarily set 0 points for the Fahrenheit and Celsius scales. We've arbitrarily set freezing point of water as 0. Does that mean it has 0 kinetic energy? No. Not at all. Not 0 randomized kinetic energy. Wasn't until much later that we figured out, hey, temperature actually has a 0. What if nothing's moving? That's 0, right? You don't have any temperature anymore. There's no heat. It's 0. And so that is actually called the Kelvin scale. You'll notice it does not have degrees, okay? Because it has an absolute 0. The degrees are there actually to tell you that it doesn't have an absolute 0. It's not an absolute scale. It's a relative scale. Okay? Just like a circle is relative, right? It doesn't have a beginning or end. Okay? Now, the Kelvin is the SI unit. This is how they compare to each other. So please don't talk too much and over. Okay? The freezing point of water is going to be 0 degrees Celsius. Real nice and easy to remember. Okay? The freezing point in Fahrenheit is 32 degrees Fahrenheit. You all know this because your cars probably went ding today and it had a little light that went up and it's telling you it's icy, right? It's cold out, look for ice. Okay? That happened at probably 34 degrees Fahrenheit because under bridges, on bridges, you're going to have 32 degrees Fahrenheit. Okay? And so 32 degrees Fahrenheit, frozen water. This would be 273 Kelvin. Okay? So 273 Kelvin is frozen water. 0 Kelvin is absolutely nothing. Okay? There is no randomized kinetic energy. No temperature. Okay. So the normal body temperatures, 98.6 degrees Fahrenheit. You all probably know that to some degree. In terms of degrees Celsius, that would be 37 degrees Celsius. If you're from anywhere but the US, you knew that. And then Kelvin, it would be 310 Kelvin. Okay. In terms of boiling water, so in Celsius, it's 100 degrees Celsius. Real easy to remember. That's the temperature water boils at. Okay. And in Kelvin, it's 373 Kelvin. Now, in terms of Fahrenheit, it's 212 Fahrenheit. You will notice that there's 180 degrees Fahrenheit between boiling and freezing water. Okay? Celsius, there's 100 degrees Celsius between those. Right? In terms of Kelvin, there's also 100 Kelvin in between those. So what happened is Celsius was invented. Celsius was used for a while. Then we realized there's an actual 0 to this. And so we didn't want to have to come up with a new difference. We wanted the thermometers to still be functional. And so we just took that 1 degree difference in Celsius. It's 1 Kelvin difference. Okay? and we just wholesale poured it over and just went down on the scale. Okay. So 0 degrees Celsius, 273 Kelvin, right? Now, what that means is for 100 degrees Celsius change, you change to 180 degrees Fahrenheit. Okay? That's how I always remember that, by the way. Okay, let's talk about converting now. Okay, so if you are in Celsius, you add 273, that's going to get you in Kelvin. Okay? If you're in Kelvin, you just subtract 273, right? And that'll get you in Celsius. Okay. If you're in degrees Celsius and you want to get into Fahrenheit, what you need to do is you need to multiply by 1.8. Okay? And then you add 32. And that will get you in degrees Fahrenheit. If you want to go the opposite way, what you need to do is the opposite of that math formula, right? And so we need to take degrees Fahrenheit, subtract off 32, and then you divide by 1.8 after you've done that problem, the subtraction. That's what that parentheses means in case it. Okay. So body temperature again. The normal body temperature is going to be 98.6 degrees Fahrenheit. This is 37 degrees Celsius. Body temperature is going to vary by person for person. If we were to measure everybody in here, we'd see probably like a 2-degree spread or so, and assuming nobody's sick. And then among your day, right? If you're out in the sun, working, running around, doing stuff, you're going to go up in temperature usually. Okay, you're outside right now, you're probably going to go down in temperature. But you can you can change something like a 2 degrees on each side and mostly be okay. You might feel a little cold, a little hot. It's oftentimes reverse what you think you should feel. But you'll still be okay. You can range up into 100 degrees and you'll be fine physically. Okay? Now, if a human body temperature rises above 40 degrees Celsius, which is 104 degrees Fahrenheit, this actually is going to be where the condition, which is hyperthermia, happens. Okay? Hyper meaning greater, thermia meaning temperature, right? And so what you're going to see here is that this can cause then convulsions. You can then slip into a coma, and you can end up with permanent brain damage from this. Okay? And so this can get very serious very fast. That's why, like, especially children, anybody that has younger siblings or children or anything like that, knows that if their fever ever gets up near 104 degrees Fahrenheit, you take them to the hospital, right? Because very dangerous.
I was going to say the definition is wrong for.
Yeah, it's wrong on this. I need to fix it. Yeah, we got a chance here. Let's see if I. Yeah, I've just copy paste, right? So I had the formatting. Okay, hypothermia. There you go. Now, so this actually is because once you get up to 104 degrees Fahrenheit, what you're doing is you're actually trying to destroy whatever's infecting you. And by raising the temperature up, what your body's hoping is that it kills that thing and stops it from functioning properly faster than it kills you and stops you from functioning. And usually that works. Sometimes it doesn't. Okay? And so what it's doing is it's actually harming your brain. So that's the important part. It does harm your heart to some degree, but that's not usually as much of an issue. Your brain is the one that's most sensitive. And so
chemotherapy, where you're trying to kill the other cells before you kill your.
It is exactly like chemotherapy, though that is poisoning instead.
Yeah.
But yeah, most things if we that are widely applicable to killing off the thing that's harming us are like that. Otherwise, we have to get super specific, and they don't work on a lot of other stuff. That's why it's very rare to find like broad spectrum antivirals and broad spectrum. Some like antivirals do not work on bacteria. Antibacterial does not work on viral.
It's like the same reason.
Neither works on fungi.
It's like why we don't have a universal cancer cure other than.
Yes. Yeah.
chemo.
Yeah. There's actually is a really good treatment method. We can talk about it sometime. That had above 80% even on terminal cases, but it is not widely deployable. Yeah, it's just yeah. You take cultures of the cancer, and you literally culture them, and then you mix up between. It depends on how good you want to do, but if you want to do really well, 14 different drugs, and then specifically target that cancer versus the cell cultures of the person you're trying to cure, and you can optimize it. And it takes a lot of money, a lot of man hours. Yeah. But they've had cure rates, and this was back in the 70s, of above 85%, even on the
So
terminal
makes
cases.
it more insane that Steve Jobs died.
Well,
It does.
Well,
that
he died
was
just because he just didn't like.
Well, sometimes he
Anyway.
tried like a fruit dye.
Yeah. He was also pretty arrogant.
It's
too.
like he had the money
Yeah.
to do that.
And Steve Jobs is a weird guy. He like a lot of these tech billionaires, they're smart in one thing, does not mean they're smart in everything.
Well, he was also like really prideful too.
Oh yeah, he was.
He never acknowledged it.
Mm.
It's like that he was wrong. Never.
Yeah, no. So body temperature drops below 35 degrees Celsius, 95 degrees Fahrenheit. This is going to be hypothermia. This is much more benign than hyperthermia in terms of as long as you don't have freezing of the water in the extremities, then you're going to usually have no real long-term effects from this unless you get cold enough to die, essentially. So you can spend days in hypothermia and revive and be totally fine. So you are weakened for a while, but you'll be like fully healthy within a weeks. So you can recover very nicely from very extended times of this. This is going to have irregular heartbeat. It has slow breathing rate. Now, the person in this condition usually feels cold at first and then hot later because their body temperature starts going down, and that's how you tell the differences, and your nerves don't work as well. But this is actually dangerous, extremely dangerous, not because of the physical results, it's because of the mental. So when you're heated up, you start hallucinating and something's really wrong, right? And you feel awful. You want to fix it. And so you do. You splash some water on you, get a wet towel, cold, something, right? Ice bath, something. When you go into hypothermia, you feel good. Like it is, after a while, you don't hurt. Just like putting cold packs on a sore spot. You don't hurt. Okay? You start becoming less and less responsive, more lethargic, right? And so it's a perfect recipe that you don't seek help, you don't do anything, you just, it's okay. Okay? And you start making really bad decisions. And so, physically speaking, hyperthermia is super threatening sound, right? And hypothermia sounds, it's not, physically speaking, as bad. Okay, so let's put a vote to it, though. What does more people die from in any given year? Hyperthermia or hypothermia? So is it more dangerous for it to be hot outside or cold outside? Let's put it this way. So is it dangerous for it to be hot if it's 150 degrees Fahrenheit outside? Okay, you probably have never experienced that. No?
150.
150.
Yeah. Yeah, that's like normal for summer in like Las Vegas area, where I laid pipe mains
Wait,
all through college.
115 or 50?
50.
Okay, that's nuts.
It gets into the 130 to 150s, and that's
Is it 150?
normal.
I feel like is where it gets to the point where they tell you like you can't be outside for longer than
They do make those announcements now. It is absolute bullshit. And it's only really
if you're overexerting.
no, that's not even true. You can't be outside if you are from a place where it doesn't normally do that. So if you're not used to it, it is lethal. If you're used to it, it's.
Well, I have a question. What's the humidity? Because I feel like that's a big factor.
Okay, so there it's low. Humidity being high would actually make it more dangerous. Yes.
Yeah, because like I was like in Egypt before, it would reach like 120 sometimes.
Mhm.
It wouldn't feel that bad just because there's like no humidity.
Mhm.
But then like over here, when it gets like 90 high humidity, it just sucks.
Yes, it does. But so
Is there science? Like, what's the science behind that? Where, like,
so the figures are about 2 to 3 times as many people die of cold each year
Mhm.
as die of heat. And in terms of the science, there's actually case studies where there's a famous magician who put himself in an oven, so 300 degrees Fahrenheit, and had a water hose going in, and he lasted several days. So you can very easily last in 300 degrees Fahrenheit. 150, I've been in 152 degrees Fahrenheit. I worked 12 hours and I laid pipe. And I mean, I'm white as white comes. I wasn't as white then, I'll tell you that. But like, you gotta acclimatize to it. I thought I was gonna die the first like week. I honestly thought I was gonna die. And I used to go down and lay the water main, and it'd get really humid when you dig down, right?
Mhm.
And so it'd be like 130, high humidity, almost 100%.
Oh wow.
And I would walk out of the hole that we were putting the water mains in, and there'd be literally the water on me would go poof. And it'd be like steam coming off me everywhere. So just like, and then it would be gone.
So that's the magic trick.
Yeah, it was a magic trick. It was wild. But yeah, I mean, I've worked in 130 to 152 degrees Fahrenheit weather. You can do very hard work running everything. Don't just all do it at once, and you need to drink lots of water.
yeah, hydration. Get super dehydrated.
People are having those strokes and heart attacks because of dehydration. They're not drinking water properly. So, which is becoming more common due to the weather change, but that's because people have not adapted. Cold, you can't do anything about.
I feel like it's hard to adapt like the weather in here just the weather's like bipolar.
Is it all, like, is there a level of it that's like we
We're actually done with the lecture.